I want to talk about and get you thinking about derivatives and the shapes of graphs. So we're just going to go, and we've done this before. We're going to go back and kind of talk about. So what I've got here is the graph of the parabola y equals x squared. And you guys are going to have to help me figure this program out on the fly here, because this is a new one. One of the old ones that I sort of depended on having is no longer supported. And so we're going to have to use this one instead, which is probably better, but I'm just not as familiar with it. So you'll probably figure it out long before I will. So here's the first derivative, graphed in light blue, I guess. What is the shape, or excuse me, that's the function. That's f of x, or y. What is the first derivative going to look like? Just take a second and just, slap down a quick sketch in your notebook and then describe it to me.
Oh, sure.
And while you're doing that, does some great soul want to remind us, what is the sort of the visual or graphical relationship between the first derivative and the function? First derivative graphs what? Slope of the function, good. Okay, so the ant has that built-in slope sensor. It's just graphing the value of the slope sensor, right? What it reads as he walks along the function. Okay? So suggestions, what's that going to look like? We've done this one, I think, even before. Okay, straight line, slanted upward, good. So increasing, right? Okay, and that makes sense, doesn't it? Because if we look at the little, and the way I would encourage you to think about this, think about it in terms of just little tangent lines, right? So as the ant's walking along, if these are the tangent lines, they're pretty steep and negative, a little less steep and negative, less steep and negative, less steep but still negative, but they're getting closer and closer to 0, right? And then they start to increase in steepness as he moves along the other side, right? And so we end up with, and let's see if we can get this to work, we end up with a second derivative. And let's see if we can do this. So, graphing, equations and functions. Okay, so now I want to do derivative with respect to x of that. Okay, that looks good. Okay, so does that make sense? And it kind of rescaled it for us. Zoomed in a little bit, yeah. It flattened it out. If we want to look at that, does that make sense? Here, let me make this proportional. So it makes it a square graph. Does that make sense? You see, that's kind of a bad color, but I don't know if I can control that. I probably can, but I'm not going to take the time to figure it out. Okay, so, boy, that is bad, isn't it? Can everybody see that green line?
Oh, yeah, I can see it.
Okay. Makes sense, right? Yeah. Okay, so let's graph the second derivative. Okay. Now, first of all, what's the second derivative going to look like? Okay, horizontal line. Where is it going with the y-intercept that is? Okay, and you gave me an exact value. Okay, it's 2. Yeah, that's true. All I really even care about is that it's positive and constant. Okay, but it is 2. So fill in the blanks here then. The behavior, the graphical behavior of the second derivative, how is that related to the first derivative? Okay, and it's the same, it's just a transferred relationship, isn't it? The value of the second derivative equals the slope of the first derivative. Okay, now here's my challenge to you for today, and we'll look at a couple examples, and we'll see if you can kind of come up with an answer, even just based on what we see in a couple different examples here. What I want to know is, what's the graphical relationship of the original function to the second derivative? Okay, that's essentially the topic of the day. Okay, is what does the second derivative do for us in terms of a description of a graph or a function? Okay, well, let's graph it here. I mean, you already know what it looks like. And then we'll just save this one. So let's see, I want a new. How do I get a new one here? Add, there we go. Thank you. Second derivative, oops. Okay.
Yeah.
Okay, and there it is, right? No big deal. If we do a proportional display, there it is.
You know, whatever. Go with that.
Okay, that's a little easier to see. Let's take a picture of that. And we'll move on. This is pretty fun playing with this thing. It really is. Okay, so now I can.
Thanks, Clayton.
Oops. So I probably want to hit remove, right? Yeah, there we go. All right.
You get Jessica.
Okay, so let's try. How about? And this will be an easy one also. Let's do negative x squared.
Oh, good lord.
Okay. I lost myself. What am I doing here? Oh, whoops, no wonder.
Okay, I was gonna say, whoa.
Whoa, not what I wanted.
That is not negative x squared.
There we go. Negative x squared. What did it do? Oh, wonderful. So how do I manage that? Okay.
That's hilarious.
Just put a bunch of negatives.
Yeah. Here, let's try this.
Out.
Let's try this. Let's try -1 times x squared. Let's try that. There we go. Okay, finally we got it. Okay. So there's my graph, and you. This is pretty obvious what's happening here. Let me just add the other parts of this real quick. So here we got derivative of. Come on. So I gotta do that. Copy. Derivative. There we go. Okay, so there's, right? Make sense? Okay. And we'll go to something a little more interesting here in a second.
I like interesting. Oh, I'm sorry.
Oh, darn it, I keep messing that up, don't I?
Oh god.
So just write a paragraph. You said page max, so paragraph minimum.
Okay, makes sense? Right? Make sense? Okay? All right. Thought so?
You go because if you go x squared, you take the derivative of that.
Okay.
2x, and the second one is x2.
Oh.
Yeah, so it goes on to line that too.
Oh.
Yeah, there we go. Baby.
Oh, that's negative.
Yeah.
I was like, that's negative.
Okay, let's try x cubed.
Yeah.
Try it.
I like the X cube ones like this.
You like those?
Yeah.
Okay, so how about this one?
X cube reminds me of a heart.
It's not actually W, still next to this.
Okay, what's the derivative of that gonna look like?
It's a parabola.
Okay,
A U.
and there's a couple ways. You guys, your insight will tell you that for many reasons now, probably. You know that if you take the derivative of a cubic polynomial, in this case a power function, you know that the derivatives are just going to knock it down by 1/2. power each time, right? To make this thing look a little tamer, how about if we put a 1/3 out in front, just so it looks a little better, a little easier to see what's going on. This is, oh, hello. This is called Microsoft Math. You can get this for your computer, I believe, for free. I don't know if it's for free. It may not be for free.
Yeah.
Oh, look at that. We got some. Oh.
That is not
Oh, it keeps doing that. Why does it keep?
God, this is fun.
Jeez. Why is it doing that?
All words that you know you spelled right.
There we go.
Bing,
Yep.
there it went again. I think this software's worth crap.
I think you're right.
No wonder it's free, it is not.
Yeah, okay. Well, here, we'll trick it. We'll just go 1/1. What's 3 cubes? So that's going to be about, how about if we do about 1.2? Yeah. 1.2 out front. That'll work. Or excuse me. 1. Let's do that. There. That'll work. Okay, that's a little better. Okay. All right. So anyway, we're going to get a parabola if we look at the function of this. You already told me that. If we look at the derivative of that, right? So of just a cubic. Okay, I'm not recommending this so heartily anymore. Thought it was going to be really cool. Not so sure.
That's so hot.
Okay. There's that one.
I need to change the color on that.
Yeah, that's not good, is it?
Yeah. No, they do have red. What's the fourth one? Is it yellow? Oh, not.
It's white.
It's good. I couldn't afford it.
Why did they have?
There we go. Okay.
Let's do a fourth derivative.
Okay.
Do a third derivative. Yeah, let's do it. I want to see that extra color.
All right.
I just want to see the color. I don't care about anything else.
Are we gonna do a third derivative?
Just messing a little bit, making it look a little better. I realize it. Okay, let's try that. That a little.
You want to look serious enough that you
See that fourth color.
Want to see the fourth color?
Yeah.
Let's try that. Oh, that's too good.
Number 17.
Let's try that. This will be good. Okay, proportional. Oh, it doesn't make that much difference. Fourth color. You just want to know what it is?
Yes, please.
Fourth.
See, as you
Fourth
go,
color.
now you think it's gonna be
Green.
How much is it? It's $5. It's worth it.
Black. Oh, okay.
I
All
was
right.
wondering why there wasn't a black.
Yeah.
Lame.
All right.
It's not even horizontal.
Can you take a fourth
Yeah.
derivative?
Okay, so what do you notice there about the second derivative? Okay, it's negative for a while and positive for a while. So what I want you to do here now, let's run through. Let me take a picture of this. We'll run through those. See if you can make some suggestions about how the second derivative is related to the original. Okay?
Second to the original,
Yeah, how the second derivative is related to the original.
so the line.
Okay?
It,
Well, it is. You're right. You're right. But what I'm interested in is how the shape of the second derivative is, or how the shape of the second derivative is related to the original function, and then how the value of the second derivative is affected I don't want to say this, how it's manifested in the shape of the original. In other words, let me give you an example. So we know that the function is increasing, right, when the first derivative is positive, right? We talked about that the other day. The original function is a decreasing function if the first derivative is negative. Fill in the blanks for me is what I want you to do. The function is what if the second derivative is positive, and the function is what else if the second derivative is negative. So just let's look at these here. I want to get this just so it's just a little bit easier to see. Like let's go negative 10 to positive 10. That's probably going to be good. Yeah, that's not bad. Okay, we'll use that. Okay. Okay, so Exhibit A. There's Exhibit A.
I wasn't even going to say it. I was just going to look at you.
And so we don't even really care here about the green function, right? We're just comparing, which is good because that's the hard one to see, right? So we're just comparing the blue original, the shape of the blue original, to the whatever that is. Is that fuchsia? Is that what fuchsia looks like? I don't even know what fuchsia looks like.
It's like a bright,
Yeah.
bright,
Oh, okay.
it's like a reddish.
Oh, okay.
So yeah.
To the
I still don't know what fuchsia is.
yeah.
I don't know either.
Okay, to the pink.
Oh yeah, I like that. That's better. Okay.
Okay, Exhibit A.
Maybe.
Focus, focus, focus. Shh, focus. Exhibit A. Exhibit B.
I feel like I'm being what?
Blue to pink.
I choose exhibit B.
Exhibit C. Blue to pink. So we want to look at the regions, and to make this a little bit easier even, we're looking at where, maybe on this one, where is the second derivative negative compared to where it's positive? Negative over there, right? So you got this interval over here.
Are you asking in terms of that?
Yeah, right? And then over here.
Because the second
Any suggestions?
It's bisecting or intersecting the maximum and the minimum, isn't it? On the first one, you see how?
Yeah, okay. Okay, true, but that's not what I'm looking for. Yeah. Because I could shift these things vertically. I mean, I could add like 7 to the original, and that would shift it up, right? Okay. Okay. So, Exhibit C, one more time, and then we'll talk about it.
Exhibit A.
Exhibit A, here we've got a positive second derivative everywhere. Notice the shape of the function, right? Here we've got a negative second derivative everywhere. Notice the blue shape. Here we got a little of both. Negative on the left, positive on the right. Any suggestions? Any suggestions yet?
I'm lost. I don't know.
Okay, I'm gonna give you a little more fuel here. We'll add a little fuel to the fire. Okay, let's look at it this way. Okay? The blue function is the original, right? If we draw in some tangent lines like we did before, we got a horizontal tangent line, they're increasing. So isn't the second derivative is just the rate of change of the first derivative, right? So it's really just the rate of change of the slope. Agreed? So shouldn't a positive second derivative, will you tell me that a positive derivative should imply that the first derivative is increasing, right?
Yeah.
Because the second derivative is the rate of change of the first derivative. Okay? Right? So now hold this thought. Don't get distracted. Think hard on this. So then, if a positive second derivative means a positive rate of change of the first derivative, in other words, the first derivative is increasing, first derivative means slope in our mind, right? So that a positive second derivative means that the slope of the function is increasing. That's not what a positive first derivative means, though, is it? An increasing function is a different thing completely. An increasing function could have a rate of change of the slope that's actually decreasing. The slope could be getting less positive, but still be increasing, right? Right? A second derivative means that the slope is actually getting more positive, right? Okay, what does that tell you about the shape of the curve? If we're kind of molding this function as we go, and the first derivatives are being increased, what does that tell you about the shape of the function? As the ant's walking along from left to right, if the function is going to have a positive second derivative, the slope of the function is going to always be increasing. It's going to be getting steeper. What does that tell you about the terrain that he's walking into?
It's uphill.
Okay, it's not only is it uphill,
Dramatically changed.
Right uphill.
yeah, wouldn't you even say that it's, well, the word we're going to use, and actually the technical calculus word is it's concave up. He's always going to see the hill in front of him increasing, right? It's going to be getting steeper and steeper.
Yeah.
Make sense? Okay. Now, if the ant is really, really short, it doesn't matter. When he looks out ahead, he's still going to see the curve in front of him, right? Okay, let's contrast that with a situation where we've got a negative second derivative. Here's our ant walking along. As he stares out along the function, what does he see that's different? Now, with the negative second derivative, the slope is decreasing as he walks along. Can he see the function in front of him?
No.
No, because he's really short. His line of sight is looking out over the top of the hill. He can't see that hill disappearing in front of him, right? And so the negative second derivative literally tells us something about the shape of the curve. It tells us that it's concave down, doesn't it? Right? Does that make sense? So so there's a couple ways to think about that. One way to think about it is, concave up is where it tends to kind of catch water if it's raining in our two-dimensional universe, right? The water's going to pool up. Concave down is going to shed water, right? Probably that's a little hokey. Probably a better definition is, how does it relate to a tangent line? Any place where the second derivative is positive, if I draw in a tangent line, like so, okay, there's a tangent line where it's positive. Compare that to a place where we draw in a tangent line where the second derivative is negative. What's the difference? I could draw a bunch of them up here. I'm always going to see the same kind of behavior. Compare that to down here. Where do the tangent lines sit relative to the curve if the second derivative is positive? Those compared to those. Say it again.
We're still positive, so.
Okay, but it wouldn't have to be. Wouldn't have to be. I could draw. Here, I'll give you an example. I could draw. It's not the actual value of the slope we're worried about, because look at this. If I draw a function like this, I could pick places like right here where the slope is negative, but still, I want you to notice something about these tangent lines, where it's concave up compared to where it's concave down.
Meaning that they're like parallel with each other?
Well, they might be, but they might not be, depending on which points I take. Where it's concave up, be blue. Concave down is red. What do you notice about all those tangent lines, the red ones compared to the blue ones? Yeah, you're gonna kick yourself for not seeing this.
The opposite of each other.
Just,
Obviously, they're doing something similar.
they're describing the same thing for sure.
It's doing something.
It helps. I feel like.
What's the difference between all?
One's red, one's blue.
Well, what about the red ones compared to the blue ones? Okay, all the red ones are on top.
More of
Yeah.
a
Oh, I
gentle.
saw that,
Right?
yeah.
All the red ones are on top and the blue ones are on the bottom. Okay, so there's probably maybe even a better graphical description. For the second derivative, if a function has a negative second derivative and is therefore concave down, all tangent lines in that region sit on top of the curve, right? If the second derivative is positive and therefore concave up,
Oh, I see.
all tangent lines sit below the
I
curve.
see. Okay.
You see it?
Yeah.
Makes sense.
Right? Okay,
Right.
now, doesn't that also imply then that there must be some point of transition, right? So what's happening at the points of transition? Okay, so let's look here. Oh, probably didn't want to quite do that, did I? Okay, so at the point of transition of our function, wouldn't you agree it seems to be concave down over there, and then up here it's concave up, and we can see that if we look at the pink second derivative function, there's the 0 right there, isn't it? Okay, that's where it changes, where it transitions, right? Where it transitions, notice that the tangent line, a different color, I guess we'll leave that one.
It's the same one.
Where it transitions, the tangent line is neither above nor below, it's it's both, right? That's what we call a point of inflection. Or an inflection point.
What's that? Where
Inflection
all the
point.
dots-
Yeah, where it's the tangent line is both positive and negative.
Okay? Make sense? All right. So is there something important? I mean, you got to know this first of all. I mean, that's just nice to know that that's the description of the second derivative. But now, is there some hidden value in this? And I'll tell you, yes. You just got to find it. Is there some real important hidden value in this concavity issue? Okay. And inflection points are important points on curves. If we do things like, for example, as we're going to do shortly, when we talk about, let's get those phones blinking. When we talk about things like, let's say economics, the calculus of economics, and we want to start to use calculus to decide how we're going to price our items to maximize profitability and things like that. Well, then we're going to actually start to take a look at what are these important points on the functions, peaks and valleys, extrema and inflection points, what do they mean? Well, what we're going to find is inflection points actually have some pretty important value because we call them points of diminishing returns, right? When you're talking about profitability, sure you want to be profitable, but you hit a point where you actually want the rate of change of your profitability to not start to decrease, because that's where you start to hit what's called a point of diminishing returns, right? For example, if you, you can invest an awful lot of resources into a company to increase profitability, but if the profitability is not going up so much, you're kind of over leveraging yourself, and you put yourself in a dangerous position where if the economy starts to turn, now you've got all this stuff invested in the company, and that's a risk. You understand what I'm saying? And so economics is really heavily built on calculus. So you don't want that. You want to get to a point where the profitability is really sensitive to changes to increases in, for example, the number of products that you're selling, so that you're at a point where small changes can increase or decrease the profitability, and so you're not as leveraged. I mean, that's probably not making total sense, but these are actually, so these functional topological things that we're talking about end up being really important when you're actually analyzing behavior of functions later on, which we'll do. I mean, that's coming up later on in this chapter. Okay, for now though, let's take a look at an example going back to the previous section where we're going to use the tables and the first derivative test to analyze a function, and then we'll superimpose the second derivative over that and say, okay, could the second derivative have made this whole process a little bit easier, maybe, right? By just knowing what the second derivative means. So let's take something like, and this will be this is metaphorically killing two birds with one stone because we're going to get to practice first derivative, the first derivative test, and introduce the second derivative test. So let's try.
When you graph like the second one, does that also show you like the critical points of that?
Okay, so one thing we're going to see is that, and it's probably worth me even mentioning right now. Remember that the second derivative has the same relationship to the first derivative that the first derivative has to the original function, right? And so you can extend all the logic that we've already used for finding relative extrema. You can extend that to the second derivative. So now instead of just saying critical numbers, we're going to have to say first derivative critical numbers. The first derivative critical numbers are the places where occur at the places where the first derivative is what two things?
Continuous and differentiable.
Well, no, but I'm looking, if we're looking for relative extrema, the relative extrema always have to occur at critical numbers. Not all critical numbers are going to pan out to be extrema, but they have to occur at critical numbers, right? Now think about the two kinds of extrema we can have, smooth, rounded, or jagged, right? So the smooth, rounded ones occur where the first derivative is 0, right? So there's one kind of critical number, right? The jagged ones occur where the first derivative is undefined, right? Okay, and we've talked about that. So there's kind of our approach to finding extrema with the first derivative test, right? We're going to find the critical numbers, and then we'll analyze those to see, if those occur where the first derivative is undefined or equal to 0, and then we'll explore those and see which ones pan out to be extrema. Okay, if I wanted to find points of inflection, right, for the second derivative, what we're going to see is that we do the very same process, only we ratchet it up by one derivative. So we'll explore the behavior of the first derivative, right, where we want to find the places where the first derivative either, when we differentiate that, right, to get a second derivative, we want to know where the second derivative equals 0 or is undefined. And those are our second derivative critical numbers. All of remember we call those points of inflection? All of the points of inflection have to occur at second derivative critical numbers, just like the extrema had to occur at first derivative critical numbers. Okay, now that's kind of just a foreshadowing. Now we'll actually watch that happen. So let's take this function.
Yeah, right.
You like that literary analogy there, foreshadowing?
In that class. Yeah. Which is a very good reason.
Okay, so there's our function. Let's use the first derivative test and find all the relative extrema here. Okay? So what do? Take the derivative, absolutely. So first thing we got to do is take the first derivative. Okay, so let's find the places where we get critical numbers, right? So first derivative, critical numbers. Whoops.
Where's the
So-
CN?
Is it undefined where? Nowhere. First derivative equals 0 when that equals 0, right?
So you take out
Yeah, so sure, we could take out a 4. So we've got the original equation, 4x cubed minus 12x squared equals 0. Why not? Now, being as we're solving an equation, right, we can always divide both sides of an equation by the same constant, right? Does that make sense? Same constant factor. So why not divide both sides by 4 to trim things down? So that makes that a 1 and this a 3. And then we could factor out an x squared. So I'm left with x squared times x minus 3, right? And so we get first derivative critical numbers where?
0 and 3.
0 and 3. Everybody see that? By the zero product property? If we just find the zeros of our two factors. Okay? So first derivative critical numbers are at x equals 0 and x equals 3. Okay? So let's go down and make our table. These tables are so important. I really want you doing these tables. Okay, so we didn't impose any domain on this function, right?
Mhm.
Are there any restrictions to our original function? Any values of x that are where it's undefined? No? Okay, so then what do we assume the domain to be?
Infinity.
Yeah, all real numbers. And we can indicate that like so. On the open interval, we obviously can't include infinity or negative infinity, they're not numbers. But on the open interval, from negative infinity to positive infinity, that's our way of saying all real numbers. Okay, let's include our critical numbers in there. Well, we had 0 and 3, so x equals 0 and x equals 3, right? If we want to use, and we found out that those are places where the first derivative equals 0, right? So we know we've got horizontal tangent lines there, okay? How are we going to use the first derivative test to determine if those are relative extrema? Okay, so we got to pick some test points, don't we, right? Remember, the advantage of the first derivative test is we don't actually have to even know what the value of the first derivative is, just the sign, right? And we've already got the first derivative conveniently written. If we put this in factored form up here, here we have to be a little bit careful, right? Because it's okay to divide by the same sign, but we really, when you're analyzing the behavior of the first derivative, you shouldn't cancel anything, because that's not an equation, it's a function. See the difference? Here we're just solving an equation to get some solutions. Up here we've got the function. If we factor this, I can pull out a 4x squared, leaving me with x minus 3. Okay? So we got that broken into factored form. We can use that factored form to analyze the sign of the first derivative at our critical numbers, or excuse me, at our test points, and just get some signs, plus or minus, on these intervals to see what's going on. So pick some values. What are our test points? Negative 1,000, okay. Okay. 4. Okay. I'm gonna pick one. How about 1? Okay. So at negative 1,000, what is the sign of our first derivative at negative 1,000? Well, 4x squared is always positive because x is being squared. It's multiplied by positive 4. So really, this is the sign of this second factor is the one that's going to dictate what the sign of the derivative is, right? So at negative 1,000, we get
Negative 1,003.
Yeah, so and we don't even care what it is, it's just negative, right?
Yeah.
So I'm going to get positive times negative is negative, okay? So here we get negative. At 1,
It's negative.
it's going to be negative, because I'm going to get positive. Everybody see that? Times negative. Gives me negative again. And up here at 4, it's going to be positive. Positive times positive, right?
Wow.
Okay, so now you tell me, what does that tell us about those critical numbers? Is this one right here an extremum?
No.
It's not,
Mm-mm.
because the function goes from decreasing to
Decreasing.
decreasing, okay? So it didn't pan out to actually be a minimum or a maximum, right? Now this one goes from decreasing to increasing, so that's going like that, right?
Mhm.
So
Maximum.
that's a
It's a minimum.
minimum. So we got 1 minimum, okay? Well, what was this thing, I wonder? Guess we'll find out. Let's take a second derivative. Okay, so what's the second derivative?
Well,
You don't have to. We can just let's go right here.
Okay, thank you.
Right. Yeah.
Much better. Second derivative.
Okay, so 12x squared minus 24x, and I cut that off a little bit, right? Everybody see that?
Yeah.
Okay, so we could go ahead and factor that. Factor out what, a 12x times x minus 2. Okay, and so we already got it factored. We can just add the second derivative critical numbers. We can do that math in our head. Is the second derivative undefined anywhere? No. Where does it equal 0?
0, 2.
0 and 2, yeah, okay. Make sense? Okay. So let's go back here then. Now what if this test point in between had just been a 2 instead? That would have worked just the same, wouldn't it?
Yeah.
Right? So let's make that a 2. Let's pretend we made that a 2 originally.
That's 2.
Okay, so we got 2 and 0, right? Those are our critical numbers. So we got shared critical numbers for the first and second derivative for this value, okay? Now I gotta add another row to my table, and I didn't really think ahead there, did I? So we'll erase this stuff.
I'm just gonna make a new table.
You get a new table?
No, I'll just add another row to my present
Oh, that's
table,
what I'm doing.
all right?
We're adding a new row.
Okay, and we'll put we'll take a look at, we'll add some information on that row. So here we had a 0 and a 0, right? So the fact that I have stacked up zeros in the F prime and the F double prime rows is telling us that this is a double critical number, right? Okay, we'll go back and analyze all this stuff in a little bit. Now, ignore those green test points. If I'm talking about let's figure out what the concavity is of the function on all the intervals surrounding these critical numbers. Well, I guess we could use this critical number. At negative 1,000, what's the sign of the second derivative?
Negative.
I'm going to get negative times negative is
positive.
positive. Okay, so the second derivative over here is going to be positive. Okay, what about in between? Well, I guess maybe we could have used that 1. We'll have to put the 1 right there.
1's back in.
Okay, so yeah, 1's back in the
1's
mix. So
back
if we
in
take
play.
this test point at 1, what is the sign of the second derivative? It's going to get positive times negative is
Negative.
negative, okay? So I got negative there. And do I need a test point up here? No, I can just use 3, right? You see that?
Mm-hmm.
Because 3 is not a critical number of the second derivative. I can use it as a test point of the second derivative. Okay?
Nice.
I'm going to put a star by that because that's an important idea. So at 3, what do we get?
Positive.
Yeah, positive times positive gives me positive. Okay, so then what does that tell us about concavity? If the second derivative to the left of this critical number is positive, it's concave. And is that concave up or down? Do you remember?
Down.
Let's go back and look.
Well, it goes from positive to negative.
So there was positive second derivative. Is that concave up or down? Up. Okay. So positive means concave up. Negative second derivative means concave down. Right? Okay, so then if we go over here, we know this means concave up, that means concave down, that means concave up, right? Now, a point of transition of the second derivative, we saw. A point of transition of the second derivative, where we went from, say, negative to positive, but it would have been the same if we had changed from positive to negative, is what we called an inflection point. Okay? Does an inflection point necessarily have to have a horizontal tangent line? No, it doesn't. Doesn't. For example, look at, well, on this one right here, how about? On this guy right here, let's I'm gonna walk along the curve as an ant, and you're gonna tell me when to make a green dot for the inflection point. Just kind of eyeballing. It's not gonna be perfect. Where we're changing concavity from up to down or down to up. So the ant's walking along. Just say stop when I get to
Stop.
right there.
Yeah.
Okay. I'm changing from
Yeah.
what to what there.
You're not. You're staying the same.
I'm really not changing concavity, am I?
No.
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 That's a relative maximum.
Yeah.
But it's not an inflection point. The concavity hasn't changed. We're still what, negative or positive?
The
Positive.
bottom.
Negative.
Negative, because it's concave down. Okay.
Because it's on top.
Okay. Yeah. So we're looking for where is it concave down, meaning where we're changing from concave down to concave up, meaning where would the tangent lines begin to transition from being on bouncing on top to underneath, right?
Stop.
Okay,
Yeah.
good, right about there, ish,
Yeah.
right? Okay, so that looks like an
Good.
inflection point because right about there is where we're transitioning from negative concavity to positive concavity, right?
I see.
You see what I'm saying?
Yeah.
Doesn't have to be a horizontal tangent line, does it? And then if we continue along, you just tell me where do we roughly get about there-ish?
No.
Sorry, a little
Kendall.
further.
Maybe a tiny bit further.
Kendall, what are you doing?
Does that make sense? Okay.
I got excited.
Well, math is exciting. Okay, so on here then, is this a point of inflection? Yeah, it is, right? How do we know?
It's a change.
Because it's a change in
Concavity.
concavity, right? That's the definition of an inflection point.
I'm totally seeing it.
Are you starting to get
Yeah.
an idea what this is doing?
Second derivative.
Exactly, because look what row we're in. We're in the second derivative row, and so we don't care what the value is. All we care about is the behavior. To the left of this critical number, second derivative critical number, the concavity is always positive, right? Remember that changes in concavity. Okay, hold that thought.
Changes what?
Changes in concavity.
Changes in concavity, dot, dot, dot.
You were going at it, now you're in.
Yes.